Hello, let us see the algorithm that is used to convert a regular expression to its equivalent DFA. This algorithm is taken from the compiler design book written by Ahulm and Shetty Lama, and this algorithm is algorithm number 3.6 in that book. This algorithm was created by Aho, who is one of the writer of the book. This algorithm was created by him in the year 1960 while he was creating a Unix command egrep or Linux Unix command egrep. So anyway, this is a fantastic algorithm. This algorithm, so here what is given, so we know that we are given with a regular expression, that is augmented regular expression. From that augmented regular expression we construct first the syntax tree. After constructing the syntax tree, we assign the position value to each of the leaf node. Then we compute the first and last pause for all the nodes. Here the first pause and last pause are written in this fashion, and after calculating all the first pause and the last pause, we find the follow pause for all leaf nodes. So that follow pause is computed at here, and in this algorithm we will see that only the follow pause, these values are required. So let us create the state table. Here state, which will hold the current state, and here we will use store the next state, and the next states are denoted by t plus 1. The algorithm start begins with finding the first pause of the root node, that is n0. The root node is this one, and the first pause of n0 is 1 to 3. So here d will contain 1 to 3. Now this 1 is basically this position, and this position correspond to a. So this 1 correspond to a, this 2 means this 2, and this 2 correspond to this b, so 2 correspond to b, and 3 means this one, and these 3 correspond to a. So you can see that the d can be partitioned into two part, 1 3 in one part and 2 in another part. So here this is our first state or starting state in our DFA, which is denoted by capital Q in the definition of DFA. So next we have to find the transition value. So we'll use the dtrans function d comma a. So here a means we will be finding the follow pause of 1 and 3 which correspond to a. So this is equal to follow pause of 1 union follow pause of 3. So follow pause of 1 can be found from this table, 1 2 3, and follow pause of 3 is 4. So finally it will be 1 2 3 4. So here we will write 1 2 3 4. Now we have to find this value next. So we have find the value for the variable a. Now for the terminal a, now we'll find the d transfer b. So b means 2. So here we have to calculate the follow pause of b, that is 2. So what is the value of 2? Follow pause of 2, that is 1 2 3, 1 2 3. So it will be 1 2 3. Now see here 1 2 3 4, this is a new state. So 1 2 3 4 d equals 1 2 3 4. Now this 1 again correspond to the a, this 2 correspond to the b, this 3 correspond to this a, and that 4, that is this 4, correspond to this b. Now we have to find this value. So d trans of d comma a. So a means 1 and 3, so it will be equals to follow pause of 1 union follow pause of 3. So follow pause of 1 is 1 to 3 and follow pause of 3 is 4. So we have to find the union of them. So it will be 1 2 3 4. So this is 1 2 3 4. Now this one. So d trans of d comma b. So b means 2 and 4. So this is follow pause of 2 union follow pause of 4. So follow pause of 2 is what? 1 2 3, and follow pause of 4 is 5. So it will be 1 2 3 5, 1 2 3 5. Now, so here 1 2 3 4, this state, the transition for this state is computed. Now 1 2 3, this is the transition for this state is also computed. Now consider this one, 1 2 3 4, the transition for this state computed at here. Now 1 2 3 5, the transition is not computed, so it's a new state. So 1 2 3 5. So our new state is 1 2 3 5. Now again, that 1 correspond to the position correspond to A, 2 correspond to B, 3 correspond to this A, and 5 correspond to this B. Now we need to find this value. So D trans of D comma A equals to, for A, so we have to find the follow pause of 1 and 3. So follow pause of 1 union follow pause of 3. So follow pause of 1 is 1 2 3, and follow pause of 3 is 4. So it will be 1 2 3 4. So here 1 2 3 4. Now this one, so D trans of D comma B. So B means 2 and 5. So follow pause of 2 and follow pause of 5. So follow pause of 2 is 1 2 3, follow pause of 5 is 6. So follow pause of 2 is 1 2 3, and follow pause of 5 is 6. So it will be 1 2 3 6. Now see, this state has been computed. Now 1 2 3 4, the transition for this state also computed at here. Now 1 2 3 6, this is a new one. So 1 2 3 6. So the state is 1 2 3 6. Now again, this 1 correspond to the A, this 2 correspond to this B, this 3 correspond to this A, and this 6 correspond to this hash. So we have to find this value. So D trans of D comma A. So A means 1 and 3. So it will be follow pause of 1 union follow pause of 3. So follow pause of 1 is 1 2 3, and follow pause of 3 is 4. So it will be 1 2 3 4. Now you have to find this value, D trans of D comma B. So B means only 2. So this is follow pause of 2. So follow pause of 2 is 1 2 3, 1 2 3. So it is 1 2 3. Now see, 1 2 3 6, this transition for this state completed. 1 2 3 4, the transition for this computed at here. So this is done. 1 2 3, it is also computed. So this is done. Now there are 1 2 3 4 different state. Now among the 4 different state, 1 2 3 is the starting state. Now which one is the last state? Now here 6, which correspond to the hash, the last symbol, that is all the state which contains 6 will be the last state or the final state. So here there is only one state, that is 1 2 3 6, this one. So this will be the last state. Now let us draw the transition diagram of this DFA. So 1 2 3, this is the start state. If we give input A, then it will move to a new state 1 2 3 4, that is this one, 1 2 3 4. If we give B, we will move to the same state, so there is no change. So in B there is no change. Now in 1 2 3 4, if we give A, there will be no change, so that is we will be in the same state. If we give B, then we will move to the 1 2 3 5 state. If we give B, then we will move to the 1 2 3 5 state. Now in 1 2 3 5, if we give A, we will move to 1 2 3 4. If we give A, we will move to 1 2 3 4. In the 1 2 3 5 state, if we give B, then we will move to the new state, that is 1 2 3 6. And this is the final state, so I am using this final state notation. Now in the 1 2 3 6 state, if we give A, we will move to 1 2 3 4 state. If we give A, we will move to the 1 2 3 4 state, and if we give B, we will move to the 1 2 3 state. So this is the DFA D, which is constructed from this augmented regular expression. So we can say that this, the language generated by the DFA D, which is LD, is equals to the language generated by L of S. So this is the algorithm. Thank you.